In this lecture, we'll be discussing the concept of the positive definite matrix. This is a very important construct in linear algebra. It's something that is typically not presented in a first course in linear algebra, but would be in a second course in linear algebra. It comes up in many different applications. Two of the most prominent applications are nonlinear optimization and multivariate statistics. So when you have a multivariate distribution, you're typically dealing with a correlation or a covariance matrix. And the concept of positive definiteness is involved. So first, recall that we have the idea of a quadratic form. Quadratic form for a matrix that's n by n, and we write that as x transpose ax for x being an n vector. And remember, x will be a column vector. So x has dimension n by 1, which means this expression is a scalar. And so the way to think of this is x is the variable. So it's a vector variable. We say that A in Rn by n, so an n by n real valued matrix A, is positive definite if that quadratic form, x transpose ax, is greater than 0 for all x in Rn such that x differs from the 0 vector. You, of course, have to omit the 0 vector from this because 0 transpose A0 would be 0. But this is the definition of a matrix being positive definite, and we see the quadratic form being the key part of the definition here. We also have a weaker version of this. We say A is positive semi-definite if x transpose ax is greater than or equal to 0 for all x in Rn. And so the only difference here is that we have the possibility that x transpose ax could equal 0 for a non-zero x in Rn. The result of this, which we can prove as a theorem, is that in the first case, if A is positive definite, then A is invertible or non-singular. Positive definiteness is actually a stronger condition than invertibility. If your matrix is positive semi-definite but not positive definite, it means that A is not invertible. It has a non-trivial null space. But this concept of positive definiteness and positive semi-definiteness is really a key concept. Another key definition that comes up regularly with positive definite matrices is the definition of matrix symmetry. So we say A, again, an n by n real matrix, is symmetric if A is equal to its transpose. And recall that the definition of the transpose of a matrix is the original matrix with its rows and columns swapped. So if A, say in the 2 by 2 case, was A11, A12, A21, A22, A transpose, this first row becomes the first column. So we have A11, and let's be careful with our indices here. We have A12. And then the second row of A becomes the second column of A transpose. And so the first entry will be A21, A22 for the second entry. So notice the result here was to reflect the entries about the main diagonal. That's how we would get A transpose from A. If your matrix A is symmetric, then these off-diagonal entries have to match. In this case, A21 and A12 would be equal. This comes up often when you deal with matrices that are positive definite or positive semi-definite. And in the examples we mentioned before, optimization, this comes up because positive definite matrices come up with a matrix version of a second derivative, and you have partial derivatives in your matrix. And because in many cases the partial derivatives of a function, say with respect to x and then with respect to y, is the same as the partial derivative of that function with respect to y and then with respect to x. So because you can change the order of partial differentiation, you end up with symmetric matrices of second derivatives. And then in statistics, multivariate statistics, then you end up with an issue with covariance. So the covariance of x and y is the same as the covariance of y and x. It's a commutative operation, and that results in symmetric covariance or correlation matrices. So we see this issue of symmetry coming up a lot. And so it's very common that we deal with matrices that are symmetric and positive definite, or symmetric and positive semi-definite. Let's look at an example for the case of n equals 2 and tinker around a bit to get a feel for what it means for a matrix to be symmetric, positive, definite. And so that's our assumption here. This is often abbreviated SPD. And since A is symmetric, positive, definite, number one, by symmetry, we know that these off-diagonal entries must be equal. So the symmetry implies that A21 and A12 are the same. So let's rewrite A exploiting this. So we have A11 and A22 on the diagonal. We have A12 here, but note that we can replace that A21 with A12, explicitly pointing out that these two entries are the same because A is symmetric. So now this A only has 3 distinct entries, at most 3 distinct entries. Now, because it's positive definite, we know by definition that x transpose AX is greater than 0 for all x in R2. So 2 vectors with 2 real entries, such that x differs from the 0 vector. So let's explore this. Let's plug in some different values for this vector x and get a feel for what it means for this matrix A to be symmetric, positive, definite. Any x in R2 that's non-zero has this property. So we can pick anything we want to get a sense of what A looks like. So why don't we try out x equals 1, 1. If x equals 1, 1, our quadratic form, x transpose AX, can be written as 1, 1 times our matrix A1, 1, A1, 2, A1, 2, A2, 2, times the column vector 1, 1. We know we can do the second multiplication first. So we have a 2 by 2 times a 2 by 1. So the result will be a 2 by 1, a vector. To get the first entry, take the dot product of the first row of A and the dot product of this vector here. So we get A1, 1 times 1 plus A1, 2 times 1. Or A1, 1 plus A1, 2. To get the second entry, we take the dot product of this second row of A with the vector 1, 1, and we get A1, 2 times 1 plus A2, 2 times 1. Or A1, 2 plus A2, 2. And then here we have a 1 by 2 multiplied by a 2 by 1. So the result will be a scalar. And we're just taking the dot product of this vector and this vector. So we get 1 times the first entry, A1, 1 plus A1, 2, plus 1 times the second entry, which is A1, 2 plus A2, 2. And we see now that because of the symmetry, these two terms combine. If A was not symmetric, we would not be able to have those combine. But we get A1, 1 plus 2 times A1, 2 plus A2, 2. And because our matrix is positive definite, this is positive. So because A is positive definite, by definition, this quadratic form for this particular value of x has to be positive. Now, we can do something interesting with this. Let's use this inequality to isolate the A1, 2 entry. So if we do that, first subtracting A1, 1 and A2, 2 from both sides, we have 2 A1, 2 is bigger than negative A1, 1 plus A2, 2. And we can divide both sides by 2, and we get A1, 2 is greater than negative 1/2 times A1, 1 plus A2, 2. And let's label this as equation 1. If we repeat the same exercise, except instead of x being 1, 1, let's choose x to be 1 minus 1. And we go through the same procedure of computing x transpose AX. What will happen is we'll get something very similar. We'll have A1, 1, 2A1, 2, and A2, 2. But the difference is we have a minus sign here, as opposed to the plus sign that we got when we did x equals 1, 1. The same approach of isolating that A1, 2. So in this case, we subtract A1, 1 and A2, 2 again from each side, and we get minus 2 A1, 2 is bigger than negative quantity A1, 1 plus A2, 2. Of course, exploiting the fact that this has to be positive. This quadratic form has to be positive because A is positive definite. So, right, take this, subtract A11, subtract A22. But now we multiply both sides by negative 1/2. And that gives us A12 on the left. Gives us a positive 1/2 on the right. But remember that the inequality reverses when we multiply it by a negative number. We can call this inequality here inequality 2. And then we can combine inequalities 1 and 2 in the following way. Inequality 1 tells us that A12 is bigger than minus 1/2 times the sum of A11 and A22. But inequality 2 tells us A12 is less than 1/2 times the sum of A11 plus A22. This tells us that the absolute value of A12 is less than the average of A11 and A22. And we will see this generalized in a moment in a theorem. But what this is telling us is that if you look at your matrix A, if you pick an entry, an off-diagonal entry, the size of that off-diagonal entry is smaller than the average of, if you go up to the diagonal entries that correspond to it. In absolute value, this off-diagonal entry is smaller than the average of these corresponding diagonal entries. So that's one interesting result. Let's pick some other convenient values for x. How about 1, 0? If x is 1, 0, then x transpose AX will be the row vector 1, 0 times our matrix A times the column vector 1, 0, which, if we work this out, doing the second product first, we take the dot product of the first row of A and the vector 1, 0. We get A11 times 1 plus A12 times 0. Or A11. To get the second entry of this product, we take the dot product of the second row of A and the vector 1, 0. We get A12 times 1 plus A22 times 0. So we're left with the vector A11 and A12. And of course now we have the dot product of these two vectors. We get 1 times A11 plus 0 times A12, or just A11. And because our matrix is positive definite, this has to be positive. Well, that means the first diagonal entry of the matrix has to be positive. Note, if we chose x to be 0, 1, the same analysis would tell us that A22 has to be positive. And this will generalize. It is the case that for a symmetric positive definite matrix, all of those diagonal entries are positive. So let's summarize what we've just seen in an example in a theorem. If our matrix A, so R in Rn by n, is symmetric, positive definite, then we have two results here. One AII is positive for I ranging from 1 to n. So all the diagonal entries are positive. And we also have the absolute value of AIJ is less than AII plus AJJ times a half. And we have some other consequences that we have not explored. We also have the maximum over I and j of the absolute value of AIJ. So this is the maximum absolute value entry. So the maximum of all the absolute values of all the entries of A occurs on the diagonal, which is also positive because the diagonal entries are all positive. So the largest entry in the matrix, the largest absolute value entry in the matrix, happens on the diagonal. And it happens to be the biggest element of the diagonal. The idea here, intuitively, is that these things tell us that A has what we often call a weighty diagonal. So if you think of the absolute values of the entries in the matrix as being something like mass, then you have the mass of the matrix concentrated on the main diagonal. That's done in the sense that all the diagonal entries are positive. If you take any off-diagonal entry in absolute value, it's smaller than the average of the corresponding diagonal entries, as we looked at here. You go for an off-diagonal entry, go over to the diagonal and up to the diagonal, average those entries, and you get something that is bigger in size than your off-diagonal entry. And the biggest entry in size on the matrix happens on the diagonal. So this is not a mathematically precise statement, but intuitively this is the idea, that a positive definite matrix, a symmetric positive definite matrix, has its weight on the diagonal. We'll look a little bit more at properties of symmetric positive definite matrices in the next lecture, but this should give us a feel of what it means